Welcome to Night Cosmos Sleep, where we slowly explore the hidden laws operating beneath the familiar world. At this very moment, the room around you seems completely stable. The bed supports your body, the walls remain still in the darkness, and the faint glow of the clock continues to mark the passage of time. Everything appears solid, clearly defined, and free of anything mysterious. But at the deepest level, this world is not built from tiny, rigid objects that always occupy fixed positions. Electrons do not circle atomic nuclei like miniature planets. Light is not entirely a continuous wave. Even the position, energy, and motion of matter can only be described as a range of possibilities governed by the laws of probability. So, why does a world built from probability not descend into chaos? How can atoms preserve their structure for billions of years? Why does matter have shape? Why does light have color? How can the sun shine steadily? And how do dead stars resist the immense crushing force of gravity? Quantum mechanics is often treated as a theory meant only for laboratories, unimaginably small particles, or complicated machines. Yet its rules are at work inside your body, in the light entering your eyes, in every molecule of air, and in the very objects supporting you right now. On tonight's journey, we will move from this quiet room into the deepest structure of matter, then follow those same laws into the core of the sun, through extremely dense stars, and toward the oldest traces of the universe. But before we look outward across those enormous distances, we need to begin with the moment the world around you creates the feeling that it is truly solid. Try placing one finger on the surface of a table near you. As your finger slowly moves downward, you feel a hard surface stop it. If you press more firmly, the table pushes back against your fingertip. The sensation is so familiar that we rarely stop to question it. Your hand is matter. The table is matter too. The two objects touch, so they cannot pass through one another. The answer seems perfectly obvious, but when we look deep inside matter, the idea of touching is no longer quite so simple. The skin on your fingertip is made of cells. Those cells are made of molecules, and the molecules are made of atoms. The table is built in much the same way, whether it is made of wood, metal, glass, or stone. At the atomic level, neither your hand nor the table resembles a continuous solid block. Both are systems made of extremely small nuclei at their centers, surrounded by regions formed by electrons. Just before you feel the surface of the table, the outer electrons in the atoms of your skin have already begun interacting with the electrons in the table's material. The two layers of matter do not press together like two solid bricks. What prevents your finger from moving farther downward is the force that emerges when electric charges and electron states are brought too close together. To imagine the scale inside an atom, we can picture the atom enlarged to the size of a stadium. In that image, the nucleus would be only a tiny object near the center of the field. The rest of the atom would extend much farther outward. The nucleus usually occupies less than 0.01% of the atom's volume, yet it contains more than 99.9% of its mass. This means that nearly all the mass of the table is concentrated inside extraordinarily small nuclei. Yet the table's size is not determined by those nuclei alone. The region occupied by electrons forms the outer boundary of each atom and influences the distance between atoms within the material. The stadium image helps us appreciate this enormous difference in scale, but it can also become misleading if taken too far. We should not imagine electrons as tiny balls flying through a completely empty stadium. The region around the nucleus is not a place where nothing exists. Electromagnetic fields are still present there, along with quantum states that determine how electrons are able to exist. An electron does not remain motionless at a single point, but neither is it distributed randomly everywhere. Within an atom, electrons can exist only in regions and states permitted by quantum laws. These regions help determine the atom's size, how it responds to light, and how it bonds with other atoms. So saying that an atom is mostly nothing is an oversimplification. It is true that the nucleus occupies a tiny volume compared with the atom as a whole, but everything outside it is not meaningless empty space. The electron region surrounding the nucleus is responsible for nearly every interaction we experience in everyday life. As your finger moves toward the table, the atoms in both objects begin to approach one another. Electrons carry negative electric charge. When their electron regions draw closer together, the electromagnetic interaction between them changes very rapidly. Charges of the same sign cannot easily be forced close together, but the force that keeps your finger resting on the table cannot be explained simply by saying that electrons repel one another. In a real material, electrons are bound to nuclei and to the material's entire structure. When you press downward, you are trying to force the electron systems in your finger and in the table to rearrange themselves. Changing those states requires energy. The material responds with a force directed against the pressure you are applying. Alongside electromagnetic interaction, there is another important quantum limit. Electrons of the same kind cannot simply be forced into exactly the same quantum state. This rule is known as the Pauli exclusion principle. Here, a state does not simply mean a position on the table. It includes the way an electron exists within a system, such as its energy and motion. When atoms are brought too close together, many electrons must change their states so that the entire system continues to obey this rule. That change requires additional energy and helps matter resist being compressed or passed through. We can imagine a room where the seats are arranged according to extremely strict rules. When only a few people are present, everyone can easily find a suitable place. But as more and more people are forced into the same area, the convenient seats are no longer available. Those who arrive later must occupy other positions that are harder to reach. Continuing to crowd more people into the room becomes increasingly difficult. This is only an image to help us understand the idea. Electrons do not literally sit in chairs. Still, it shows why matter cannot be compressed into the same space without limit. Nature restricts how identical electrons can be arranged, and that restriction is one of the reasons matter possesses rigidity. When your hand rests on the table, gravity is still pulling your hand and your entire body downward. But the table does not allow your hand to keep falling. It produces an upward force that balances the downward force your hand applies. On a large scale, we experience this only as a surface supporting the body. On a much smaller scale, it is the result of countless atoms responding to one another. Electrons change states. Bonds within the material are compressed by extremely small amounts. Electromagnetic fields transmit force through the structure of the table. Each individual change is far too small for us to notice, but when trillions upon trillions of atoms participate together, the result becomes a force strong enough to keep your hand above the surface. The same thing happens when you sit in a chair. Gravity pulls your body downward, causing the seat to deform by a tiny amount. The atoms in the material are brought closer together and respond with an upward force. When that force balances the weight of your body, you remain seated. But remaining still does not mean that everything has stopped moving. The atoms in your body and in the chair continue to vibrate. Electrons remain in their quantum states. Air molecules keep colliding with your skin and the surface of the chair. The stability you feel is simply a balance among many movements and interactions occurring at the same time. When you stand on the floor is also compressed by a very small amount. The force from your feet travels into the material below, continues through the layers of the building, and eventually reaches the ground. Each part of that chain responds through tiny changes in the distances and states between its atoms. When you hold a cup of water, the atoms in your hand do not touch the atoms of the cup in the sense of two perfectly solid surfaces pressing directly together. Their electron regions interact, creating the forces that allow your fingers to grip the cup. If friction is strong enough, the cup does not slide downward. When you loosen your hand, the gripping force weakens, and gravity pulls the cup toward the floor. Every sensation of weight, pressure, hardness, and support begins with processes occurring at distances far smaller than the human eye can see. This also helps explain why different materials have different degrees of hardness. A pillow can be compressed easily, while a wooden tabletop is more rigid, and a sheet of steel is even more difficult to deform. The difference is not that the atoms in steel are solid in a completely different way from the atoms in a pillow. It comes from how atoms, molecules, and electrons are arranged, bonded, and able to respond when a force is applied. In a pillow, much of the visible change comes from air being pushed out and from fibers bending or sliding past one another. In wood, molecular networks hold the structure together more firmly. In metal, Electrons and atoms form a structure that allows force to be transmitted in a different way. Whether a material is soft or hard, the foundation remains the same: the way its particles and electron states respond when they are brought closer together or forced to change their relative positions. But this raises another question. If nearly all of an atom's mass is concentrated in its nucleus, why is the size of an object determined mainly by its electron region? The nucleus is extremely heavy compared with an electron, but it is far too small to create the familiar size of matter on its own. It is the electron states that determine how far an atom extends outward. The outer electrons also determine how closely one atom can approach another before the system begins resisting that approach. The shape of an object, then, depends on more than where its mass is concentrated. It also depends on the energy states electrons are allowed to occupy and on how those states change when many atoms come together to form a material. If we ignore this and imagine atoms only as solid spheres, we cannot fully explain why matter has size, why different elements possess different properties, or why some materials are soft while others are extremely hard. Nor can we simply imagine that removing the empty space inside atoms would allow all matter to be compressed into an extremely small volume without resistance. Under intense compression, electron structures change, quantum states become filled, and other forces begin to matter. In extreme conditions, matter can enter states completely unlike anything we encounter in this room. In ordinary life, we do not need to think about any of this each time we place a hand on a table. Our senses simply tell the brain that a surface is present and that the hand cannot move any farther. But beneath that simple sensation lies a system organized with extraordinary precision. The table does not need a stone-like atomic shell to prevent your hand from passing through it. Hardness emerges from the way electrons and electromagnetic fields respond when atoms are brought too close together. Electromagnetic interactions create force. Quantum rules restrict how electrons can be arranged. Countless tiny responses combine to form a surface strong enough to support your hand, a cup, your body, and everything else resting upon it. So when your finger touches the table, what you feel is not two layers of perfectly solid matter pressing directly against one another. You are feeling the resistance of electrons that cannot easily be pushed into different states. But to understand more clearly how electrons create the boundaries of atoms, we must let go of a very familiar image. Electrons circling the nucleus in neat paths like planets orbiting the Sunday. In many textbooks, a hydrogen atom is drawn in a very simple way. A proton sits at the center, while a tiny electron circles it along a neat, round path. This illustration helps readers quickly recognize the basic structure of an atom, but it can also create a misleading intuition. An electron is not a miniature planet, and the region where it exists around the nucleus is not an orbit that can be drawn as a continuous line. If we continue to imagine the electron as a tiny ball following a definite path, many observations from the atomic world become extremely difficult to explain. In everyday life, the motion of an object can usually be tracked quite clearly. A car traveling along a road always has a particular position, direction, and speed, whether anyone is watching it or not. From that information, we can estimate where the car will appear after a certain amount of time. An electron cannot be fully described in this familiar way because quantum mechanics does not give it a continuous trajectory like the path of a car or the orbit of a planet. Instead of a fixed path of motion, science describes the electron with a probability map. This map tells us which regions around the nucleus are more likely to contain the electron and which are less likely. If many identical atoms are prepared and the same measurement is performed on each one, the electron may be detected at a different position every time. Yet after enough measurements, the results do not scatter randomly. They gradually form a stable pattern that matches the distribution predicted by quantum mechanics. We can loosely imagine this as a dark room where a faint sound is being produced, though its source cannot be seen. After listening for only a moment, you may not be able to determine exactly where the sound is coming from. But after listening many times under the same conditions, you could create a map showing where the sound is most often detected at its strongest. This image helps convey the idea of a region of possibilities, but it still does not fully capture the difference between quantum probability and ordinary lack of information. When we do not know which drawer contains a key, the uncertainty exists only in our knowledge. The key is still resting in one definite location, even if no one has opened the drawers to check. With an electron, the state before measurement is not simply treated as a tiny particle already sitting at an unknown point. That state is genuinely described by a collection of possibilities, and the measurement gives us one specific result from among those allowed possibilities. This does not mean that an electron can appear anywhere in the universe without restriction. Its distribution is limited by the atom, by the energy of the system, and by extremely precise quantum laws. There are regions where the electron is often detected, regions where the probability of finding it is very low, and even places where the probability is zero. A probability map is therefore not a chaotic cloud of fog. It is a clearly structured form that can be calculated and tested through experiments. These structured states are known as orbitals. The name may sound similar to an orbit, but an orbital is not a path traveled by an electron. It is a quantum state describing how the electron is distributed around the nucleus, while also containing information about its energy and other properties within the atom. An orbital can be represented by regions of varying density, with darker areas indicating a higher probability of detecting the electron when the measurement is repeated many times. Some orbitals are shaped almost like spheres surrounding the nucleus, while others extend into several regions pointing in different directions. Between these regions, there may be locations where the electron is almost never detected. These shapes are not rigid shells or physical rooms that hold the electron inside. They are simply visual ways of representing the structure of a state that cannot be observed directly with the human eye. In an atom containing many electrons, each electron must be arranged according to specific rules. They cannot freely enter any state they choose, nor can they coexist in every arrangement we might imagine. The orbital structure creates different layers and regions of energy around the nucleus, determining how the atom responds to other atoms. This invisible arrangement will later help give rise to the periodic table, chemical bonds, and countless properties of the matter surrounding us. The electron's energy, like its position, is also restricted. In the familiar world, a car can accelerate gradually through many different speeds, while an object being lifted can stop at almost any height. An electron inside an atom cannot take on energy across a continuous range in this way. It is allowed to exist only in certain states with specific energy levels, and the spaces between those levels are not places where the electron can remain stable. Energy levels are often pictured as the steps of a staircase. A person can stand on a lower step or move to a higher one, but cannot remain suspended in the space between them. This comparison is useful only for illustrating the discontinuous nature of energy, because an electron does not literally climb upward or downward through space like someone on a staircase. A higher level simply means that the state contains more energy. It does not necessarily mean that the electron has moved farther from the nucleus along a particular straight path. When an atom receives the appropriate amount of energy, an electron can transition from a lower state to a higher one. The energy supplied must match the difference between the two permitted levels, rather than having just any value. If the energy does not match, the electron will not make that particular transition. The process is somewhat like a lock responding only to a key of the correct shape, even though an atom contains no literal lock or key. Under many ordinary conditions, a high-energy state does not last very long. When the electron returns to a lower state, the difference in energy may be released as a photon. The photon carries exactly the amount of energy corresponding to the gap between the two levels, so the emitted light appears only at certain frequencies. From a process taking place inside an atom, visible colors and other forms of radiation begin to emerge, ready to be measured by instruments. This phenomenon can be observed by supplying energy to a gas containing separate atoms. The electrons in the gas are raised to higher states, then emit light as they return to lower ones. When that light is separated into its components, it does not form a continuous band of color. Instead, it appears as a series of distinct lines. Each line corresponds to a particular energy difference between two states within the atom. Every element has its own nuclear and electron structure, so each one produces a characteristic group of spectral lines. Hydrogen has one pattern, helium has another, while sodium, iron, and calcium each leave their own distinctive signatures. These patterns can be regarded as the fingerprints of the elements, because by examining the bright or dark lines, scientists can identify the type of atom that emitted or absorbed the light. In this way, the composition of matter can be determined without touching it directly. This ability is especially important in astronomy, where most objects are far too distant for humans to collect physical samples. Light from a star may travel through space for hundreds or thousands of years before reaching a telescope on Earth. When separated into a spectrum, that light reveals characteristic lines created by atoms within the star. From a very faint beam, humans can determine whether the star contains hydrogen, helium, iron, or many other elements without ever leaving their planet. Even sunlight carries a network of dark lines across its familiar band of colors. Certain wavelengths have been absorbed by atoms in the sun's gaseous layers because the photons carried energies that matched electron transitions. Those tiny, dark gaps become sources of information about the composition of a celestial body located roughly 150 million kilometers from Earth. What we read in the light ultimately begins with extremely small energy levels inside atoms. The quantum states of atoms not only allow us to analyze distant stars, but also provide the foundation for measuring time on Earth. In a mechanical clock, time is divided by the motion of a pendulum or a set of gears, while electronic clocks often rely on the vibration of a quartz crystal. Atomic clocks go further by using an exceptionally stable energy transition within an atom. Because of that stability, the same type of atom can provide nearly identical reference rhythms in laboratories located far apart. 1 second in the International System of Units is defined by 9,192,631,770 cycles of radiation, corresponding to a hyperfine transition in the cesium-133 atom. Scientists do not watch an electron complete a certain number of revolutions around the nucleus and then call that interval 1 second. Instead, they direct radiation with an extremely precise frequency at cesium atoms, then observe how readily the atoms transition between two states. The frequency that produces the strongest response is maintained as the reference rhythm by which the system measures time. A cesium atom does not know which country it is in, nor does it change its rules simply because it has been placed inside a different device. When conditions are properly controlled, atoms of the same kind respond to the same frequency. This consistency allows laboratories around the world to maintain a shared standard of time with extraordinary precision. A quantum property hidden inside the atom has therefore become the invisible rhythm that keeps every second of modern society in agreement. That precision is essential for telecommunications, computer networks, scientific observation, and satellite navigation systems. When a phone determines its position, it compares the arrival times of signals transmitted by several satellites. Because those signals travel at the speed of light, even a very small timing error can become a significant error in distance. Quantum rules that seem confined to the interior of atoms are therefore quietly supporting navigation, data synchronization, and the connection of systems across the planet. But why can an electron not possess just any amount of energy? One simple way to approach this question begins with the wave-like nature of the electron's state. When a string is held at both ends and set into motion, it cannot sustain every imaginable pattern of vibration. It can produce only those patterns that fit the length of the string. In a similar way, an electron state around a nucleus must satisfy certain conditions, so only particular stable shapes and their corresponding energy levels are allowed to exist. An electron is not a material string vibrating around the nucleus, so this comparison serves only to clarify the underlying principle. The important point is that energy levels are not arbitrary numbers chosen by nature and assigned to atoms. They emerge from the structure of quantum states and from the ways those states can exist stably around a nucleus. States that do not satisfy the necessary conditions do not form lasting levels that an electron can occupy for an extended period. The division of energy into distinct levels has consequences that reach far beyond a single atom. It determines how electrons are arranged, how atoms bond with one another, which forms of light matter can absorb, and which colors objects reflect toward our eyes. The red glow of a lamp, the dark lines in the sun's spectrum, and the reference rhythm of an atomic clock are all connected to the same principle. The world possesses clear structure, partly because electrons are not free to carry just any amount of energy. Quantum mechanics can predict the probabilities of these outcomes with remarkable accuracy. When a system is prepared in the same way, and a measurement is repeated many times, the distribution of results closely matches the calculations of the theory. Yet a deeper question remains. If the state before measurement contains many possibilities, why does each measurement produce only one specific result? This is where the ability to predict experimental outcomes and the question of the theory's deepest meaning do not completely overlap. Many interpretations of quantum mechanics have been proposed to approach this problem, but our journey does not require us to choose a single explanation. What matters is that quantum mechanics describes with great precision which outcomes can occur and how frequently they appear, while the question of why one particular result becomes the observed reality is still debated. The lack of a complete agreement about interpretation does not weaken the accuracy of predictions that have already been tested. It simply shows that using a theory successfully and fully understanding what that theory means are two different tasks. An electron, then, does not travel along a fixed circle like a planet, but neither does it wander freely around the nucleus. It exists in states with clearly defined shapes, energies, and probability distributions, and it can transition between them only when these restrictions give rise to spectra, color, atomic structure, and the precise rhythms of time used by modern society. Yet they also lead us toward an even more important question about the existence of matter itself. A negatively charged electron is always attracted to the positively charged nucleus. If it does not move along a fixed orbit that keeps it at a distance, as a planet remains in orbit around the Sun, there seems to be nothing preventing it from falling directly into the center. And yet, atoms preserve their stable structures throughout the matter around us, from air and water to the human body. To understand why atoms do not collapse, we must look more deeply at the limits quantum mechanics places on the electron's position, motion, and energy. 1 second in the International System of Units is defined by 9,192,631,770 cycles of radiation, corresponding to a hyperfine transition in the cesium-133 atom. Scientists do not watch an electron complete a certain number of revolutions around the nucleus and then call that interval 1 second. Instead, they direct radiation with an extremely precise frequency at cesium atoms, then observe how readily the atoms transition between two states. The frequency that produces the strongest response is maintained as the reference rhythm by which the system measures time. A cesium atom does not know which country it is in, nor does it change its rules simply because it has been placed inside a different device. When conditions are properly controlled, atoms of the same kind respond to the same frequency. This consistency allows laboratories around the world to maintain a shared standard of time with extraordinary precision. A quantum property hidden inside the atom has therefore become the invisible rhythm that keeps every second of modern society in agreement. That precision is essential for telecommunications, computer networks, scientific observation, and satellite navigation systems. When a phone determines its position, it compares the arrival times of signals transmitted by several satellites. Because those signals travel at the speed of light, even a very small timing error can become a significant error in distance. Quantum rules that seem confined to the interior of atoms are therefore quietly supporting navigation, data synchronization, and the connection of systems across the planet. But why can an electron not possess just any amount of energy? One simple way to approach this question begins with the wave-like nature of the electron state. When a string is held at both ends and set into motion, it cannot sustain every imaginable pattern of vibration. It can produce only those patterns that fit the length of the string. In a similar way, an electron state around a nucleus must satisfy certain conditions, so only particular stable shapes and their corresponding energy levels are allowed to exist. An electron is not a material string vibrating around the nucleus, so this comparison serves only to clarify the underlying principle. The important point is that energy levels are not arbitrary numbers chosen by nature and assigned to atoms. They emerge from the structure of quantum states, and from the ways those states can exist stably around a nucleus. States that do not satisfy the necessary conditions do not form lasting levels that an electron can occupy for an extended period. The division of energy into distinct levels has consequences that reach far beyond a single atom. It determines how electrons are arranged, how atoms bond with one another, which forms of light matter can absorb, and which colors objects reflect toward our eyes. The red glow of a lamp, the dark lines in the sun's spectrum, and the reference rhythm of an atomic clock are all connected to the same principle. The world possesses clear structure partly because electrons are not free to carry just any amount of energy. Quantum mechanics can predict the probabilities of these outcomes with remarkable accuracy. When a system is prepared in the same way and a measurement is repeated many times, the distribution of results closely matches the calculations of the theory. Yet a deeper question remains. If the state before measurement contains many possibilities, why does each measurement produce only one specific result? This is where the ability to predict experimental outcomes and the question of the theory's deepest meaning do not completely overlap. Many interpretations of quantum mechanics have been proposed to approach this problem, but our journey does not require us to choose a single explanation. What matters is that quantum mechanics describes with great precision which outcomes can occur and how frequently they appear, while the question of why one particular result becomes the observed reality is still debated. The lack of a complete agreement about interpretation does not weaken the accuracy of predictions that have already been tested. It simply shows that using a theory successfully and fully understanding what that theory means are two different tasks. An electron, then, does not travel along a fixed circle like a planet, but neither does it wander freely around the nucleus. It exists in states with clearly defined shapes, energies, and probability distributions, and it can transition between them only when the appropriate conditions are met. These restrictions give rise to spectra, color, atomic structure, and the precise rhythms of time used by modern society. Yet they also lead us toward an even more important question about the existence of matter itself. A negatively charged electron is always attracted to the positively charged nucleus. If it does not move along a fixed orbit that keeps it at a distance, as a planet remains in orbit around the sun, there seems to be nothing preventing it from falling directly into the center. And yet atoms preserve their stable structures throughout the matter around us, from air and water to the human body. To understand why atoms do not collapse, we must look more deeply at the limits quantum mechanics places on the electron's position, motion, and energy. Suppose an atom truly behaved like the familiar picture found in textbooks, with a tiny electron orbiting the nucleus the way a planet circles the sundial. The electron carries a negative charge, while the nucleus carries a positive one, so the electric attraction is always pulling the electron toward the center. According to classical physics, a charged particle moving along a curved path must also radiate energy, causing its orbit to shrink more and more. Eventually, the electron would spiral into the nucleus, and the atom would lose its structure. If that were what actually happened, the matter around us could not survive for long. The atoms that make up air, water, the tabletop, and the human body would continually collapse into smaller structures. Chemistry would never have enough time to develop. Molecules could not preserve their shapes, and the familiar world would disappear before it ever had a chance to emerge. Yet real atoms have remained stable in nature for billions of years, showing that the image of an electron moving along a classical orbit cannot be the whole story. The attraction between the electron and the nucleus is still entirely real. It is this force that keeps the electron bound within the atom instead of allowing it to drift freely into space. An electron with more energy can exist in a more extended state, while an electron that loses energy usually transitions into a state closer to the nucleus. Even so, this downward journey does not continue forever, because the atom permits only certain energy levels. At the end of that sequence lies the ground state, the lowest energy level the electron is allowed to occupy. An electron can release energy as it moves from a higher state to a lower one, but once it reaches the ground state, there is no lower state into which it can continue falling. No solid wall stops the electron. Nature simply provides no suitable state beneath that level. The image of a ball rolling toward the bottom of a bowl can partly help us picture this process. The ball may move lower and lower from the sides of the bowl, but once it reaches the bottom, there is nowhere lower for it to go. Yet, the ground state of an atom is not a real bowl, and the electron does not become a motionless marble sitting at the exact center. Even at the lowest possible energy, the electron's state remains spread across a region surrounding the nucleus. That spread is part of the reason an atom has size. The electron does not occupy one precise point while quietly moving around the center. Instead, it is described by a state with its own width, shape, and probability distribution. The ground state of a hydrogen atom is concentrated more strongly near the proton, but it does not shrink entirely into the proton. Even this tiny structure preserves a natural separation between the electron region and the nucleus. The origin of that separation lies in the way position and motion are connected in the quantum world. For a large object, we usually assume that it always has an exact position and velocity, even when our instruments are not good enough to measure both. An electron does not follow that familiar intuition. Quantum mechanics places a fundamental limit on how precisely position and momentum can be defined at the same time. This limit is known as the uncertainty principle. The name sometimes leads people to imagine that nature is merely hiding information from us, or that human instruments are still too crude. In reality, this is not a flaw in measurement. The more tightly an electron state is confined in space, the broader its range of momentum must become, and that relationship is built directly into the structure of the theory. Think of a very brief sound lasting only an instant. To create a pulse that is tightly confined in time, many different frequencies must be combined rather than using a single steady tone. A quantum state has a similar relationship. The more tightly we try to confine it within a small region of position, the more momentum components must be combined. The comparison is not exact, but it helps show why forcing an electron into a point would not make it calmer or more motionless. If the electron state were compressed into an increasingly small region around the nucleus, the uncertainty in its momentum would grow. A broader range of momentum means that the state carries more kinetic energy. Excessive confinement, therefore, does not create a lower energy, more stable state. Instead, it raises the energy of the entire system. The atom reaches a balanced size where both the electric attraction and the energetic cost of compressing the electron are taken into account. The uncertainty principle is not a new repulsive force acting alongside the electric force. It does not produce an invisible stream of energy that pushes the electron away from the nucleus, nor does it behave like a spring placed at the atom's center. A more accurate description is that states confined too tightly have higher energy, so they cannot be the ground state. The electron maintains a finite region of distribution because the energy structure of the whole system permits that balance. From this perspective, stability no longer means complete stillness. A stable atom is not one in which every component has stopped moving, but one that has reached a state from which it cannot spontaneously lose more energy and descend any lower. The electron still has a momentum distribution, still interacts with light, and can still transition into another state if it receives the appropriate amount of energy. Stability lies in the durable structure of the system, not in absolute immobility. Even the lowest state does not turn the electron into a particle resting motionless inside the nucleus. Its probability region still extends around the center and retains a definite shape. If a photon arrives carrying exactly the right amount of energy, the atom can absorb it and raise the electron to a higher state. The electron may later return to a lower level and release energy, but the final stopping point remains the ground state, not a location inside the nucleus. For a hydrogen atom with only one electron, the balance between electric attraction and the structure of the quantum state is enough to create a stable atom. Heavier atoms contain many electrons and must satisfy an additional requirement. Their electrons are drawn inward by the nucleus, repel one another electrically, and are not allowed to arrange themselves in every imaginable way. A principle that applies specifically to identical particles begins to create a new form of order. The Pauli exclusion principle states that two electrons within the same system cannot occupy exactly the same quantum state. This does not simply mean that two electrons cannot stand in the same place like two marbles that cannot overlap. A quantum state also includes the electron's energy, the shape of its distribution, and its spin. Only when all the relevant properties are identical does the Pauli restriction become impossible to violate. Imagine a theater divided into several tiers of seats, with each group able to hold only a limited number of people. Those who arrive first may occupy the lower and more convenient seats, but once those places are filled, later arrivals must move to higher levels. Electrons do not literally sit in chairs. But this image helps explain why every electron in an atom cannot crowd into the lowest energy state. From this arrangement, electron shells gradually emerge. The lowest states are filled first, and later electrons enter higher states according to specific rules. This pattern changes as the number of protons and electrons increases from one element to the next. The periodic table is therefore not merely a list of elements arranged by mass. It also reflects the quantum order of electrons surrounding the nucleus. The electrons in the outermost shell are especially important because they are the first to interact with other atoms. The way this outer shell is filled determines whether an element readily accepts electrons, gives them away, or tends to share them in chemical bonds. Oxygen, carbon, sodium, and the noble gases have very different properties not only because their nuclei contain different numbers of protons, but also because their outer electrons are arranged in distinct patterns. The Pauli principle also gives matter an additional resistance to compression. When atoms are forced closer together, their electron regions begin to overlap more strongly. The electrons cannot all crowd into lower states that are already occupied, so some must move into states with greater momentum or energy. The more the material is compressed, the greater the energetic cost becomes, and the more strongly the matter responds against the force being applied. Even so, no single rule can take full credit for keeping atoms stable. Electric attraction binds electrons to the nucleus. Quantum structure creates the ground state. The uncertainty principle limits how tightly an electron can be confined, and the Pauli exclusion principle arranges multiple electrons into different states. In larger atoms, repulsion between electrons and many other effects must also be considered. The stability of matter emerges from the way this entire system works together. A bridge does not remain standing because of a single steel beam, and an atom does not survive because of one principle alone. Each part of the structure plays a different role, from the electric attraction at the center to the order of the outer electron shells. When all these rules act together, the atom settles into a low-energy state with a stable form and the ability to endure over immense periods of time. From this delicate balance, the material world gains the foundation it needs to exist. Low temperatures do not completely erase quantum activity. As a system is cooled, thermal motion decreases and its particles move closer to their lowest possible energy state. Yet reaching the ground state does not mean that everything becomes perfectly motionless. The spatial width of quantum states, their momentum distributions, and certain quantum fluctuations remain even after most thermal disturbance has disappeared. A crystal near absolute zero still cannot be described as a collection of atoms resting completely still at fixed points. Their positions retain a degree of quantum spread, while the crystal lattice can still preserve the lowest vibrations allowed by the structure of the system. These are not tiny marbles shaking in the ordinary sense, but signs that even the lowest energy state has its own structure and activity. The stability of the world, then, does not come from every particle finding a place of absolute rest. It arises because nature permits only certain states and prevents states that are too confined, too repetitive, or lower than the allowed minimum from existing. An electron can move closer to the nucleus, but it cannot collapse into a single point without causing its energy to rise sharply. Many electrons can belong to the same atom, but they cannot all occupy one completely identical state. Because of these limits, more than 100 elements can preserve their own structures and display different properties. Some elements react easily, while others are almost inert. Some conduct electricity well, while others can form long and complex molecular chains. All of this begins with the way electrons are held around the nucleus and how they fill the states that nature allows. Once atomic structure becomes stable, the electrons in the outer shells are no longer part of the story of only one isolated atom. They can interact with nearby nuclei, change their distributions, be transferred, or spread across several atoms at once. From these new arrangements, chemical bonds emerge and begin building the first molecules. Water, air, proteins, DNA, and scent all require an atomic foundation stable enough to endure. The quantum world does not stop after preventing electrons from falling into the nucleus. It continues by using those same electrons to connect atoms with one another. In this familiar room, One of the closest signs of that transition from physics into chemistry may begin with the aroma of a cup of coffee slowly drifting through the air. A hot cup of coffee resting on a table can change the entire room before you take your first sip. Warmth rises from the surface, a thin mist appears above the rim, and the aroma gradually reaches your nose. That scent does not come from the water vapor itself, but from hundreds of volatile molecules that have escaped from the coffee, mixed with the air, and begun drifting along tiny currents moving through the room. Each molecule carries its own shape, size, and distribution of electric charge. When these molecules enter the nose, some can bind to compatible receptors on smell-sensing cells, producing signals that travel to the brain. The aroma of coffee, therefore, does not exist entirely inside the cup, nor does it sit fully formed in the air like a visible color. It emerges from the encounter between molecules, receptors, and the nervous system receiving their signals. Beneath that encounter lies the arrangement of electrons. The nucleus contains nearly all the mass of an atom, but the electrons in the outer region determine which other atoms it can bond with, how strongly it reacts, and what kinds of light it absorbs. The nucleus determines whether an element is carbon, oxygen, or hydrogen, while the electrons determine how that element participates in the chemical world when it meets other atoms. When two atoms approach each other, their electron regions begin influencing one another before the nuclei can come close. The electron state of the entire system changes, and in certain arrangements, the total energy can become lower than it was when the atoms remained separate. When a new and more stable state forms, the atoms can remain bound at a particular distance. This is the foundation of a chemical bond. People often say that atoms want to have 8 electrons in their outer shell, but nature does not truly possess desires in that sense. The octet rule is simply a useful introductory way to predict the behavior of many familiar elements. The deeper explanation lies in the energy structure of the entire electron system. A bond forms when a new distribution creates a suitable state that is often lower in energy under the conditions being considered. In a covalent bond, electrons are no longer described as belonging exclusively to a single nucleus. Their states can extend across 2 or more atoms, creating a shared bonding region. The atoms are not connected by tiny hooks pulling them together. Instead, the new distribution of electrons makes the molecule as a whole more stable. The distance between the nuclei settles, where attractive and repulsive forces reach a balance. Changing even a small part of the way atoms are connected can greatly alter the properties of a molecule. 2 molecules containing the same kinds and numbers of atoms can sometimes have entirely different effects if those atoms are arranged in different shapes. A group of atoms pointing in another direction, or a bond placed in a different location, can change how the molecule enters the body, attaches to a receptor, or participates in a reaction. This shows that chemistry depends on more than a list of ingredients. 3-dimensional shape, flexibility, and the distribution of charge across an entire molecule all matter. A molecule may fit a receptor, somewhat like an object fitting into an opening of a particular shape, but the real interaction is not as simple as a rigid key entering a rigid lock. Both the molecule and the receptor can move, bend slightly, and influence one another as they approach. Among the elements that build life, carbon plays a special role because it can form many stable bonds in several different directions. Carbon atoms can connect into long chains, close into rings, or create complex 3-dimensional structures. Hydrogen, oxygen, nitrogen, sulfur, and many other elements can then attach to these frameworks, producing an enormous variety of organic molecules. Carbon's flexibility does not come from any mysterious quality, but from its electron structure. Its outer electrons allow carbon to form several bonds that are stable enough to preserve a structure, yet varied enough to participate in chemical reactions. From small molecules in the air to sugars, fats, proteins, and DNA, carbon provides a framework that can be assembled in countless ways while still obeying the same quantum laws. Alongside carbon, water is essential to nearly every process of life. A water molecule consists of 2 hydrogen atoms bonded to 1 oxygen atom, but its electrons are not distributed evenly across the molecule. Oxygen attracts the electron region more strongly, giving one side of the molecule a partial negative charge, while the other side carries a partial positive charge. This uneven distribution makes water a polar molecule. Because of this polarity, water molecules can attract one another and interact with many kinds of ions and other molecules. Water becomes an effective environment for countless reactions inside cells, while also helping transport substances, regulate temperature, and preserve the structures of large biological molecules. These remarkable abilities do not begin because water somehow knows how to support life, but because of the way electrons are arranged around the 3 small nuclei in each molecule. DNA can also exist only because of interactions made possible by electrons. This molecule consists of an extremely long chain whose components are arranged in a particular order, creating information that cells use to build and maintain the body. The 2 strands of DNA hold their structure together not through mechanical locks, but through many chemical interactions that are strong enough to provide stability, while still allowing the strands to separate when the cell needs to copy its information. Proteins reveal the importance of molecular shape even more clearly. A chain made of small units can fold into a highly specific 3-dimensional structure, and that structure determines what the protein can do. It may become an enzyme that assists a reaction, a receptor that receives a signal, or part of a tissue that supports the body. Even a small change in the sequence or surrounding environment can sometimes cause a protein to fold differently and lose its original function. Returning to the cup of coffee, the molecules entering your nose do not carry labels saying roasted or caramel. Each molecule simply interacts with certain receptors to different degrees, depending on its shape, charge, and flexibility. The brain receives a combination of signals from many types of receptors, then builds the overall experience we call the aroma of coffee. This familiar sensation begins with molecular chemistry and requires no unverified, mysterious quantum mechanism. The colors around us also arise from the way electrons respond to light. When photons enter a material, their energy may be absorbed by electrons if it matches one of the transitions the material allows. Photons that are not absorbed may pass through, scatter, or reflect back toward the eyes. The combination of wavelengths reaching the retina creates the colors interpreted by the brain, even though an individual atom does not possess color in the same way a large object appears colored before us. A leaf appears green because pigment molecules inside it interact with different parts of sunlight. Chlorophyll strongly absorbs certain wavelengths, especially in the red and blue regions, while more green light is reflected or transmitted. The green we see is therefore the portion of light that the molecular system does not use as strongly in the same way, rather than a fixed layer of green paint hidden inside each atom. The absorbed light energy can begin the process of photosynthesis. Photons change the electron states within pigment molecules, and the energy is then transferred through an organized sequence of reactions. Eventually, the organism uses that energy to create chemical compounds capable of storing it for longer periods. From sunlight, plants build matter, and that energy continues through the food chain to most living organisms on Earth. There is no need to assume that every step of photosynthesis depends on some special quantum phenomenon beyond ordinary chemistry. The fact that electrons absorb photons, change states, and participate in molecular reactions is already enough to show that quantum mechanics lies at the foundation of the process. A leaf is not a mysterious quantum computer, but it does use the fundamental quantum laws of light and matter to transform energy into chemistry. The same principles are also present in phones, computers, and many devices operating around us. Inside a semiconductor, electrons are allowed to occupy only certain ranges of energy, while between them lie energy gaps where electrons cannot exist in a stable way. By choosing particular materials and adding very small amounts of other elements, engineers can control how electrons move through this structure. Transistors use this ability to control the flow of electrons, switching electrical signals on and off or adjusting them. Billions of tiny transistors arranged inside a single chip can perform calculations, store data, and process images. These devices do not operate through miniature gears, but through the energy structure of materials, a structure that can only be fully understood through quantum mechanics. From the aroma of coffee to DNA, from the green color of a leaf to the screen of a phone, electrons do not change their nature to suit each role. The diversity emerges from how they are arranged within different atoms and molecules. The same small set of fundamental rules can create fragrance, conductive materials, living tissue, and millions of reactions unfolding quietly inside the body every second. The nucleus provides mass and determines the identity of an element, but electrons open the door that allows an atom to enter the chemical world. They form bonds, shape molecules, and control how matter responds to light. When electron states change, energy can be absorbed or released, sometimes in the form of a photon that leaves the atom and continues its journey through space. Light, then, does more than make a room easier to see or reveal the green color of a leaf. It carries energy between quantum states, emerging from atoms, being absorbed by molecules, and traveling across immense distances. To follow that journey, we must turn to another question. Is light truly a spreading wave, a stream of moving particles, or something that does not fully resemble any familiar image? From a small source of light in the room, a photon departs and begins its journey through space. If we imagine it as an extremely tiny marble, we might assume that it must follow one single path from the place where it was emitted to the place where it is absorbed. But when light is sent through carefully designed experiments, the results appear as alternating bright and dark bands, like the traces left by overlapping waves. From that moment, the simple image of a particle of light is no longer enough. Familiar waves can spread outward, meet one another, and either reinforce or cancel each other. When two wave crests overlap, the disturbance becomes stronger. When a crest meets a trough, they can weaken one another. This phenomenon is called interference, and it can be observed in water, sound, and many other oscillating systems. Light produces similar interference patterns, showing that it cannot be understood only as a stream of classical particles traveling along separate paths. Yet light is not entirely like a continuous wave spread evenly through space. When it interacts with matter, light energy is exchanged in distinct quantities called photons. An atom does not necessarily absorb an arbitrary portion of a photon and allow the remainder to continue onward. In many processes, the photon transfers its entire amount of energy to the system, or it is not absorbed in that way at all. These two aspects are not personalities that light chooses between. Light does not sometimes decide to behave like a wave and at other times decide to behave like a particle. The problem is that neither the classical wave nor the classical particle picture can fully describe everything experiments reveal. In the modern view, a photon is understood as a quantum excitation of the electromagnetic field, not as a tiny marble of light with a definite surface and trajectory like an everyday object. One of the clearest demonstrations of the limits of classical intuition is the double-slit experiment. Light is directed toward a barrier containing two narrow openings, with a screen behind it recording where the photons arrive. If light consisted only of tiny marbles passing through one slit or the other, we might expect two bright regions behind the two openings. Instead, when both paths are open and the conditions are properly controlled, many alternating bands of light and darkness appear on the screen. This pattern shows that the possibilities associated with the two paths contribute to the same interference result. At certain locations, the quantum amplitudes reinforce one another, making the photon more likely to be detected. At others, they cancel, making the photon unlikely to appear. What is being added and subtracted here is not two photons colliding, but different possibilities within the quantum state. The story becomes even more difficult to picture when the light is weakened until photons pass through the apparatus one at a time. Each time, the screen records only a small point at one particular location, much like the mark of a particle. No complete pattern of bright and dark bands appears immediately. Yet after the experiment is repeated many times, the individual points gradually gather into the same interference pattern that a wave would produce. Each photon is detected in one place, but the distribution of many results is influenced by the entire arrangement of the experiment. This combination of a single localized event and an interference-based probability pattern prevents light from being forced into either classical picture. It does not spread its energy as a thin layer across the entire screen, yet neither does it behave like a marble that secretly chose one path in advance and quietly traveled through it. If the apparatus is changed so that it can determine which slit the photon passed through, the interference pattern may disappear. This is sometimes described as though the photon realizes it is being watched and immediately changes its behavior. That language is misleading. No human observer needs to be present, and the photon possesses no awareness. It is enough for information about the path to be recorded in the apparatus or the surrounding environment. Once that happens, the relationship required for interference has been altered. A photon may interact with a detector, a gas atom, or any part of the environment capable of preserving a trace of its path. When the different possibilities become linked with distinguishable environmental states, they can no longer interfere as easily as they did before. What weakens the pattern is not the act of looking with human eyes, but the emergence of physical information about the path. The important boundary lies in interaction, not consciousness. Light was once treated as a special case, but similar behavior was eventually discovered in matter. Electrons can produce diffraction and interference when they pass through crystals or double-slit systems. Atoms and molecules can also be prepared in ways that reveal quantum wave patterns. Objects we normally think of as clearly defined particles of matter cannot be fully described by classical trajectories either. In quantum mechanics, matter has a wavelength associated with its momentum. For large objects, such as a ball, a chair, or the human body, this wavelength is so small that it cannot be directly observed under ordinary conditions. But for electrons, atoms, or carefully controlled molecules, the wave-like behavior can become clear enough to produce interference. Wave properties, then, do not belong exclusively to light. Experiments have extended this effect to organic molecules containing as many as 430 atoms and more than 1,000 internal degrees of freedom. Such a molecule is no longer a simple particle, but a structure composed of many nuclei and electrons, with internal vibrations and rotations. Despite this complexity, the entire molecule can still produce interference when it is isolated well enough from the environment. This result challenges the intuition that wave behavior belongs only to electrons or other extremely small objects. The molecule is not taken apart into hundreds of atoms, with each component following a separate path. The motion of the molecule's center of mass participates in the interference state. In other words, the entire complex structure is described by possibilities that can overlap within the experiment. What preserves the interference pattern is not the simplicity of the molecule, but how effectively it is protected from interactions that reveal information about its path. This leads to an unavoidable question. If a molecule containing hundreds of atoms can still display wave behavior, where does quantum mechanics end? Perhaps that question places the boundary in the wrong location. There is no conclusive evidence that quantum laws suddenly stop working once an object exceeds a particular size. The more practical issue is how difficult it becomes to isolate large and complex states. An electron can be held in a vacuum, cooled, and shielded from many outside influences. A chair, by contrast, is constantly struck by air molecules, reflecting light, emitting thermal radiation, and transmitting vibrations into the floor. Every interaction can carry information about its state into the environment. Because the number of interactions increases rapidly with size and complexity, delicate interference effects disappear from observation almost instantly. Light and matter also display another feature that is difficult to express through everyday intuition: quantum entanglement. Two or more systems can be prepared in a shared state so complete that each part cannot be fully described as an entirely independent object. When one part is measured, its result is correlated with the result obtained from the other. These correlations can be stronger than any simple local hidden variable model would allow. This does not mean that one particle sends an instantaneous signal to the other, telling it which result must appear. Each individual measurement still produces an outcome that the observer cannot control at will. The correlation pattern becomes visible only when data from both sides are brought together and compared through ordinary communication. Entanglement, therefore, provides no way to send controlled messages faster than light. The importance of entanglement lies in the fact that the state of the complete system contains information that none of its individual parts carries on its own. Two systems may be separated by a great distance and still be described by a shared quantum structure rooted in the way they were created or interacted in the past. This is not an invisible cord pulling two particles together, but a form of correlation deeper than classical physics predicts. These phenomena do more than challenge intuition. Entanglement and interference are being used in quantum sensors, where extremely small changes in magnetic fields, acceleration, or time can be measured with great sensitivity. Quantum key distribution uses the properties of measurement to detect interference with a communication channel. Quantum computers use superposition, interference, and entanglement to process certain kinds of problems differently from conventional computers. However, quantum computers are not machines that make every calculation faster. For many familiar tasks, classical computers remain far more efficient, affordable, and practical to operate. Quantum advantage appears only in certain algorithms and suitable types of problems, while controlling noise and correcting errors remain major challenges. Practical applications must therefore be judged by specific results, not by promises that quantum technology will replace every system in use today. Laboratories continue to push interference experiments toward objects of greater mass and complexity. Each advance requires better vacuum control, more precise cooling, and fewer interactions with light or thermal radiation. So far, no clear size has been confirmed as the point where quantum mechanics comes to an end. As a system grows larger, preserving its delicate state simply becomes more difficult. Some models suggest that an objective physical collapse process may exist, causing a quantum state to transform on its own into one definite outcome when mass or complexity exceeds a certain threshold. These proposals make testable predictions, so they are being compared with increasingly precise experiments. At present, no widely accepted result has demonstrated that such a mechanism has been observed. The question of the ultimate limit of superposition remains open. Whatever the final answer may be, experiments have made one thing clear. The simple division between waves and particles does not fully reflect nature. A photon is not merely a tiny marble of light. An electron is not merely a small particle traveling along a definite path. And a molecule does not lose its quantum character simply because it contains many components. Every system is described by a quantum state, and the way that state appears depends on the measurement and on how strongly the system interacts with its environment. Waves and particles, then, are not two boxes from which nature must choose only one. They are two classical images that help describe different aspects of a deeper reality. When energy is detected at a particular point, the result has a particle-like quality. When possibilities spread out and interfere, the behavior has a wave-like quality. Quantum mechanics holds both within a single framework, without turning the system into a familiar classical object. Inside the room, a photon from the clock display may travel through the air before being absorbed by your eyes, the walls, or another object. Electrons within a material may receive energy, change states, and later emit another photon. These processes happen too quickly and at scales too small for our senses to follow each event, yet they quietly create the light, color, and images we see. Behind a peaceful scene, countless quantum possibilities are exchanging energy. Those possibilities do more than interfere with one another. Under certain conditions, a quantum state can also extend into regions that classical physics considers impossible to cross. A particle may not have enough energy to overcome a barrier in the ordinary way, yet the probability of finding it on the other side is still not exactly zero. This phenomenon does not violate the conservation of energy, nor does it involve a literal tunnel being carved through matter. Deep within the sun's core, positively charged protons repel one another as they draw closer. Most do not possess enough energy to overcome the electric barrier completely in the classical way. Yet their quantum states still allow a very small probability that they will come close enough. Each individual chance is almost insignificant, but inside a star containing an immense number of protons, that tiny probability is repeated without end. From a passage that seems nearly impossible, the light of the entire solar system has been sustained for billions of years. Sunlight reaching a window takes a little more than 8 minutes to travel from the surface of the sun to Earth. That distance spans nearly 150 million kilometers. But the true journey of its energy began much earlier, deep inside the star's core. There, protons must come close together in an extreme environment, even though they all carry positive charges and constantly repel one another. From the perspective of classical physics alone, most of these encounters would seem almost incapable of producing nuclear fusion. The sun is not a ball of fire burning through chemical reactions like wood in a furnace. It is an enormous sphere of plasma, where temperatures are so high that electrons have separated from atomic nuclei, and electrically charged particles move freely. The entire star is held in a delicate balance. Gravity pulls matter inward, while pressure from the hot plasma and the energy produced in the core push outward. When these forces remain balanced, the Sun can maintain a relatively stable size for an extraordinarily long time. Deep near the center, the temperature reaches about 15 million degrees Celsius, while the density is roughly 150 grams per cubic centimeter. These conditions create an environment where matter is compressed far more intensely than anything familiar on Earth. Protons move at tremendous speeds and collide constantly, but high speed alone is still not enough. Before the strong nuclear force can bind them together, the protons must approach within an extremely small distance. The problem is that every proton carries a positive electric charge. When two protons are far apart, the electrical repulsion between them is not yet overwhelming, but as they draw closer, the resistance rises rapidly. We can imagine them trying to climb opposite sides of an invisible electrical hill, with the summit representing the amount of energy required to overcome the Coulomb barrier. Most protons in the Sun's core do not have enough energy to cross that summit in the classical way. If we consider only the average energy of the protons, the Sun would not seem hot enough to sustain nuclear fusion at the rate we observe. Some protons in the high-energy tail of the distribution can approach more closely than others, but even then, the electrical barrier remains enormous. This is where quantum mechanics enters the story, not as a miracle that breaks the rules, but by describing the proton differently from a tiny marble following a clearly defined path. In quantum mechanics, a proton is not treated only as a point occupying one exact position. Its state has a certain spread, and part of its amplitude can extend into a region that classical physics considers impossible to enter. So even when a proton lacks enough energy to climb completely over the barrier in the ordinary way, there is still a very small probability that it may be found on the other side. This phenomenon is known as quantum tunneling. The word tunneling can make it sound as though the proton digs a secret passage through the hill. In reality, no physical tunnel is created, nor is there an empty passage through which the particle travels like something moving underground. The image of a ball and a hill only helps illustrate the difference between classical and quantum outcomes. In the quantum description, the particle state can extend into the forbidden region and sometimes produce a result on the far side of the barrier. Nor does the proton temporarily borrow extra energy and then repay it later in the everyday sense. That phrase is often used as a quick explanation, but it can create a false impression about energy conservation. Quantum tunneling does not allow a particle to violate this law. What changes is the way we describe the probability of finding the particle in a region, not whether the proton receives a temporary supply of energy from nothing. When two protons appear close enough together, the strong nuclear force can begin to play a role. This force acts over extremely short distances and can overcome electrical repulsion once the particles approach closely enough. Yet, quantum tunneling is not the only factor that allows the reaction to occur. Temperature, density, velocity distribution, the number of collisions, and the nature of the nuclear forces all contribute to the complete process. The probability that any particular pair of protons will react is extraordinarily small. A proton in the Sun's core may undergo countless close encounters without ever fusing. This slowness is extremely important, because if fusion occurred too easily, the Sun would consume its fuel much more rapidly. The star might shine with tremendous intensity for a short time and then exhaust its hydrogen before the planets had a chance to maintain stable conditions. The Sun contains an immense number of protons, so an event that is rare for any individual pair still becomes a continuous process when repeated throughout the entire core. Every second, about 600 million tons of hydrogen enter the chain of fusion reactions. Of that amount, roughly 4 million tons of mass are converted into energy. This enormous figure emerges from countless individual events, each with a very small probability, but occurring within a dense ocean of particles. The first step in the proton-proton chain is also the slowest. Two protons approach closely enough to interact, and then one proton transforms into a neutron through the weak interaction. The result is a deuterium nucleus containing one proton and one neutron, along with the release of a positron and a neutrino. We do not need to follow every particle level detail to understand the central idea. Hydrogen is gradually being transformed into heavier nuclei. The deuterium can then combine with another proton to form helium-3, releasing a high-energy photon. In later stages, helium-3 nuclei meet and eventually produce helium-4, while returning some protons to the reaction chain. When the entire process is added together, 4 original protons have contributed to the formation of one helium nucleus, but the mass of the final product is slightly less than the total mass at the beginning. That difference in mass does not disappear. It is converted into energy through the relationship between mass and energy. The released energy appears in several forms, including particle motion, radiation, and neutrinos. From an extremely small difference in each reaction, the Sun produces enough power to illuminate the entire planetary system. The neutrinos created in the core are barely held back at all. They interact with matter so weakly that most can pass through the Sun's dense layers and escape in a very short time. Trillions of solar neutrinos pass through your body every second without leaving any sensation you can feel. Detecting a small fraction of them has allowed scientists to examine directly the reactions taking place in a region that no telescope can see with ordinary light. Radiant energy follows a completely different journey. A high-energy photon in the core does not fly directly to the surface and then continue toward Earth. The solar plasma is far too dense, so photons are repeatedly absorbed, scattered, and re-emitted, changing direction each time and often changing energy as well. This entire process can take an extremely long time before the energy finally reaches the star's outer layers. Because of this long sequence of interactions, we cannot point to a photon of sunlight touching a window and say exactly which individual reaction in the core created it. The energy has passed through countless particles and states before leaving the Sun's surface. The final photon that reaches an eye or the ground no longer carries a simple history leading directly back to one particular pair of protons. What we can say with confidence is that its energy belongs to the flow that began with reactions in the core. When the energy reaches the convection zone, it continues upward through the movement of hot plasma. Hotter material rises, gradually cools, and then sinks again, creating an enormous circulating system. Eventually, the energy escapes from the photosphere as visible light and many other forms of radiation. From there, a photon needs only a little more than 8 minutes to cross the space between the Sun and Earth. Some of that light reaches a leaf and is absorbed by pigment molecules. The photon's energy changes electron states, beginning a chain of reactions that allows the plant to create energy-rich chemical compounds. Photosynthesis therefore connects sunlight directly to food, wood, seeds, and most of the organic matter on the planet's surface. A rare quantum process in the core of a star leaves its trace in every leaf. Solar energy also causes water to evaporate from oceans, lakes, and moist soil. Water vapor enters the atmosphere, forms clouds, and eventually returns to the surface as rain or snow. The water cycle does more than provide fresh water. It also transports heat and helps shape the weather. Behind an ordinary rainfall lies energy that began in reactions between protons millions of kilometers from Earth. Differences in temperature created by sunlight also set the air in motion. Regions warm at different rates, changing atmospheric pressure and producing winds, air currents, and many weather patterns. The oceans absorb and redistribute heat, helping create different climates across the continents. The Sun does not directly determine every gust of wind or every storm, but it supplies the main source of energy for most movement in the atmosphere and oceans. Most of the energy in food can also be traced back to sunlight. Plants store chemical energy, animals eat plants, and that energy continues through other levels of the food chain. Even many fossil fuels began with ancient organisms that once absorbed energy from the sunday. In this way, a very small quantum effect in the core of a star has passed through countless stages to appear in our meals, our body heat, and every movement we make. The slowness of nuclear fusion is just as important as its ability to occur. If quantum tunneling and conditions in the core cause the reactions to proceed much faster, the Sun would shine more intensely, but live a shorter life. If the probability were significantly lower, the star might not generate enough energy to balance gravity or maintain its present brightness. The Sun exists within a delicate range of balance, where quantum probability helps determine the rate at which its fuel is consumed. That balance is not completely fixed. Throughout the Sun's lifetime, the composition of its core gradually changes as hydrogen is converted into helium. The way energy is produced, along with the temperature and density of the core, also changes over time. The Sun remains in a relatively stable stage today, but its usable fuel is not infinite. Like every star, it exists within a cycle that has a beginning, a period of evolution, and an eventual end. At present, gravity continuously compresses the Sun inward, while pressure from the hot plasma and the energy released by nuclear fusion resists that collapse. Both sides are always acting, yet the star does not convulse violently because they remain close to equilibrium. If the reaction rate in the core decreases, the pressure falls as well, allowing gravity to compress the core more strongly. That compression raises the temperature, which can accelerate the reactions again and create a long-term self-regulating mechanism. This mechanism helps prevent the Sun's brightness from changing chaotically from one day to the next. A small fluctuation in the core does not immediately cause the entire star to go dark or erupt. The Sun's structure responds across long timescales, preserving a relatively stable environment for its planets. Life on Earth has developed beneath the light of a star whose activity unfolds with this slow and enduring rhythm. Quantum tunneling, however, should not be treated as the sole explanation for sunlight. Without high temperatures, protons would not move fast enough to approach one another frequently. If the density were too low, there would not be enough encounters. If the strong nuclear force did not operate across short distances, or if the weak interaction did not permit the necessary transformation, the proton-proton chain could not continue. The light of the Sun is therefore the result of many conditions coming together. Gravity creates the pressure and temperature within the core. The plasma provides an immense number of particles. The distribution of velocities produces a wide range of collisions, while quantum mechanics preserves a small probability of crossing the electrical barrier. No single factor can create the entire star on its own, but quantum tunneling is the part that opens a passage forbidden by classical physics. A very small probability becomes a stable source of energy because it is repeated an unimaginable number of times. Each individual reaction is insignificant on the scale of a star, but trillions upon trillions of events occurring together create a continuous flow of energy. The light beyond the window, the green of a leaf, the water vapor inside a cloud, and the energy within the body all lie at the end of a long chain that began with rare encounters between protons. Within a living star, quantum mechanics helps release energy and maintain enough pressure to balance gravity. But as the fuel in the core is gradually exhausted, that source of pressure cannot preserve the old structure forever. The stellar core begins to contract. Its density rises, and matter is forced into increasingly extreme conditions. At that point, quantum tunneling is no longer the only prominent rule. The same restrictions that once arranged electrons within atoms begin to appear on a much larger scale, creating a form of pressure that does not require the fire of nuclear fusion to exist. From tiny particles, nature can build a resistance strong enough to support the remaining core of an entire star, or determine that gravity is still powerful enough to pull it into further collapse. In the distant future, the Sun will no longer preserve the calm, stable form it has today. Hydrogen in its core will gradually run low, the rate of energy production will change, and its internal structure will begin moving through new stages. After expanding, shedding its outer layers, and exposing the remaining core, the Sun will end its life as a white dwarf. This object will be only about the size of Earth, yet it will retain most of the mass of a star. A white dwarf no longer produces energy through nuclear fusion as the Sun does today. It simply continues radiating its remaining heat and slowly cools over time. Yet this dense core does not immediately continue collapsing under its own gravity. A supporting pressure remains even after the nuclear fire at the center has gone out. That pressure does not come from hot gas, but from the way electrons are forced to arrange themselves inside matter, compressed to an extreme degree. In a living star, gravity constantly pulls every layer of matter toward the center. Nuclear fusion heats the plasma and creates outward pressure, allowing the star to remain in balance. These opposing tendencies act continuously without completely canceling each other, like two sides holding a structure at precisely the size it needs to maintain. When the energy source in the core weakens, thermal pressure is no longer as strong as before, and gravity begins to gain the advantage. As the core contracts, its density rises rapidly. Nuclei and electrons that once moved through a much larger volume are now forced into a far smaller space. If matter obeyed only classical physics, this compression might continue as the particles were pushed closer and closer together. But electrons are not marbles that can be stacked without limit, because they must still obey the Pauli exclusion principle. This principle once helped arrange electrons into shells within atoms. Inside a white dwarf, it appears on a vastly larger scale, as enormous numbers of electrons are compressed into an extremely confined region. Low-energy states cannot accept an unlimited number of electrons. Once the most favorable states are filled, the remaining electrons must occupy states with higher momentum, even as the star's temperature gradually falls. A crowded theater can help us picture part of this process. The seats closest to the stage fill first, while later arrivals must move to higher rows whether they want to or not. In a white dwarf, the seats are not physical locations, but permitted quantum states. As more and more electrons are confined within the same volume, they are forced into states with greater momentum, raising the energy of the entire system. From this compulsory arrangement emerges electron degeneracy pressure. It is not pressure created because hot particles collide more violently at high temperatures. Instead, it arises from the quantum structure of identical electrons. Even as the white dwarf cools, the electrons cannot all fall into the same lowest state. Keeping them distributed among many different states gives the star the ability to resist further gravitational compression. This distinction is extremely important. An ordinary gas loses pressure as it cools because its particles move more slowly and collide less forcefully. A white dwarf also cools, but its primary supporting mechanism does not disappear in the same way. The structure of the electron states remains, because the Pauli principle does not depend on how hot the matter is. As a result, the stellar core can maintain a size close to that of Earth for an extraordinarily long time. The density of a white dwarf is far greater than that of any ordinary material around us. A mass comparable to the Sun is compressed into a sphere with a radius similar to Earth's. Under these conditions, atoms in their familiar form no longer exist as separate structures the way they do in a table or a rock. The electrons form a shared environment, while the nuclei are embedded in matter so dense that the distances between them are far smaller than in ordinary material. Even so, electron degeneracy pressure cannot resist gravity under every possible condition. As the mass of a white dwarf increases, gravity becomes stronger and forces electrons into states with increasingly greater momentum. Beyond a certain threshold, increasing their momentum no longer produces pressure quickly enough to preserve a stable structure. This limit lies near 1.4 times the mass of the Sun and is commonly known as the Chandrasekhar limit. That number is not an identical boundary in every situation, because composition, rotation, and other conditions can influence the true structure of a star. Still, it reveals an important principle. The quantum mechanism supporting a white dwarf has a limit. Below the appropriate threshold, electrons can help balance gravity. Once the mass exceeds that capacity, the core must transform into another state or continue collapsing. A white dwarf in a binary system can sometimes draw matter from its companion star. If its mass approaches critical conditions, reactions may ignite violently and, under the right circumstances, lead to a supernova explosion. In stars whose cores are already more massive, collapse follows a different path. When the fuel is exhausted and the core exceeds the supporting capacity of electrons, gravity compresses the matter into even more extreme conditions. Under this immense pressure, electrons and protons can combine to form neutrons, releasing neutrinos in the process. Familiar atomic structure is destroyed, and the core contracts rapidly. The outer material falls inward, and may then be thrown back into space in a supernova explosion. At the center, the remaining object may become a neutron star, only a few dozen kilometers across, yet containing more mass than the Sunday. If a neutron star were placed on the map of a city, the entire object might extend across an area comparable to an urban region. Yet its mass would exceed that of the star, illuminating the daytime sky. Its matter is compressed so intensely that a teaspoonful is often said to weigh more than 1 billion tons if it could somehow remain under the appropriate conditions. This comparison is only meant to convey the density, because neutron star matter could not be removed and placed stably on a table like a sample of rock. What prevents a neutron star from continuing to contract is not merely a simple version of neutron degeneracy pressure. Neutrons also obey the Pauli principle, so they cannot occupy identical states without restriction. At these extreme densities, however, nuclear forces between particles and many other effects also become critically important. The true structure of a neutron star results from quantum mechanics, nuclear physics, and general relativity working together. The outer region of a neutron star may consist of a solid crust made of extremely neutron-rich nuclei immersed in a sea of electrons. Deeper inside, the pressure rises and matter transforms into structures that laboratories on Earth cannot sustain for long. Farther toward the interior, neutrons become dominant, but describing the entire star as nothing more than a sphere of neutrons would overlook many complex components and states. At the boundary between the crust and the core, nuclei may be stretched into elongated shapes, sheets, or tubes by the competing effects of nuclear and electric forces. These structures are often described with names resembling different kinds of pasta, though they are neither food nor familiar material. Deeper still, neutrons may form a superfluid state, while protons may display superconducting behavior in certain regions according to current models. The deepest core remains one of the great questions in astrophysics. It may contain mostly neutrons and protons in an extraordinarily dense form, but it is also possible that unusual particles appear there, or that the internal components of protons and neutrons behave in a different way. Science does not yet know with certainty which phases matter passes through as the density rises far beyond that found in ordinary atomic nuclei. The relationship between pressure and density inside a neutron star is described by its equation of state. If the matter produces strong pressure when compressed, the star can maintain a larger radius. If the matter is easier to compress, the same mass will form a smaller star. Because the exact composition of the core is still unknown, scientists measure the masses and radii of neutron stars to gradually eliminate models that do not fit the observations. These measurements are far from easy. Neutron stars are extremely small, often located hundreds or thousands of light years from Earth, and their surfaces cannot be observed like those of nearby planets. X-rays emitted from hot regions, the motion of a star within a binary system, and the way gravity bends light all provide clues. Each new result narrows the range of possible states of matter that may exist inside. Gravitational waves provide another way to observe them. When two neutron stars orbit one another and eventually collide, tidal forces distort their shapes shortly before the merger. The degree of deformation depends on the internal structure of the matter, so the gravitational wave signal carries information about the stiffness of the neutron stars. Light and the elements created after the collision provide additional evidence that no single type of observation could reveal on its own. Some neutron stars rotate extremely quickly and possess powerful magnetic fields. Charged particles around them are accelerated, producing beams of radiation that emerge near their magnetic poles. If the magnetic axis is not aligned with the axis of rotation, these beams sweep through space like the light from a lighthouse. Each time a beam points toward Earth, telescopes detect a regular pulse, which is why these objects are known as pulsars. The pulses of some pulsars are so stable that they can serve as natural clocks in the sky. Yet sudden changes can still occur inside a neutron star. Its rotation rate may occasionally increase slightly in an event called a glitch, possibly connected to the way the internal superfluid exchanges angular momentum with the crust. These tiny changes provide a rare window into a structure that cannot be observed directly. Neutron stars bring quantum mechanics and gravity together in the same place. The Pauli principle prevents identical particles from collapsing into a single state. Nuclear forces shape matter at extraordinary densities, and general relativity describes a gravitational field so intense that light is visibly bent around the surface. No laboratory on Earth can maintain a large quantity of matter under such conditions for direct study. A rule first introduced through the arrangement of electrons inside atoms now helps determine the size of an entire celestial body. In a white dwarf, electrons are forced into different states, creating pressure that resists gravity. In a neutron star, the principle governing identical particles continues to play a role, but now within an environment of powerful nuclear forces and extreme space-time curvature. Quantum mechanics does not become less influential simply because an object grows larger. Even so, not every stellar core finds a stable balance. If the collapsed core is too massive, even the supporting mechanisms inside a neutron star may not be enough. Gravity continues pulling matter inward, and a black hole may form. The boundary between the heaviest neutron stars and the lightest black holes remains an active area of research because it depends directly on the state of ultradense matter, which science does not yet fully understand. From the living sun to a cooling white dwarf, and then to a rapidly rotating neutron star, the structure of a star is always the result of a balance. Nuclear fusion can provide pressure during the earlier stages, while quantum rules continue supporting the core after its fuel has been exhausted. As mass crosses each new limit, matter must find another way to exist or allow gravity to continue its work. The presence of quantum mechanics on astronomical scales introduces a new paradox. If electrons, atoms, and even entire stellar cores obey quantum laws, there is no simple reason to claim that those laws apply only to small objects. So why does the chair in the room not appear in several places at once? Why does a mountain not produce interference, fringes, and why does the moon not behave like a wave spread across space? Perhaps quantum mechanics never disappears as objects grow larger. Perhaps what changes is the way those objects interact with light, air, heat, and everything around them. A molecule in a laboratory can be kept almost completely isolated, but a chair is constantly leaving traces of its state throughout the environment. To understand why the familiar world appears so stable and clearly defined, we must follow what happens when a quantum state is no longer kept entirely to itself. The chair in the room has remained in the same place since you entered. It is made of atoms, electrons, and particles that all obey quantum mechanics. Yet the chair does not appear on two sides of the room at once, nor does it create interference fringes across the floor. Even before anyone looks at it, it still leaves a clearly defined position in space. What happens between a molecule that can produce interference in a laboratory and the familiar object standing before us? The answer is not that quantum mechanics works only for very small objects and then suddenly stops when something reaches a certain size. So far, no fixed boundary of that kind has been confirmed. Electrons, atoms, molecules, and every component of the chair still obey the same fundamental laws. The important difference lies in how long each system can preserve a delicate quantum state before interacting with its surroundings. For interference to occur, the different possibilities within a quantum state must maintain a very precise relationship. We can picture them as wave rhythms that must remain in phase, so they can reinforce or cancel one another. If that relationship remains intact, an interference pattern may emerge after many measurements. Even a small amount of information leaking into the surroundings can prevent those possibilities from combining in the same way. In a laboratory, a small molecule can be placed inside a vacuum chamber to reduce collisions with air. The equipment can be cooled to limit thermal radiation, while outside light is carefully controlled so it does not reveal the molecule's path. Because of this isolation, the state can preserve its phase relationships long enough to produce interference fringes. The entire experiment is somewhat like trying to preserve a very faint sound inside a room that is almost completely silent. The chair has no such protection. Trillions upon trillions of air molecules constantly collide with its surface. Light from a window or lamp reflects from it in every direction, while the chair itself emits thermal radiation. Its legs transmit vibrations into the floor. Its surface absorbs and releases heat, and every atom inside it interacts with neighboring atoms. There is no moment when the chair is truly separated from the room. Each tiny interaction carries away some information about the object's state. A photon reflected from the chair may continue toward a wall, a human eye, or another object, carrying a trace of the location where it struck. An air molecule that changes direction after colliding with the chair preserves a similar piece of information. As countless traces spread into the environment, the chair's quantum possibilities are no longer contained within an isolated system. This process is known as quantum decoherence. It does not mean that quantum mechanics has disappeared from the chair or been replaced by an entirely new set of laws. What is lost is the ability to observe interference between the object's different states. The phase relationship that once allowed possibilities to reinforce or cancel one another becomes dispersed throughout such a vast environment that recovering it is nearly impossible. A drop of ink falling into a glass of water can help us picture part of this spreading process. At the moment it touches the water, the ink still has a relatively clear boundary and shape. After a short time, it stretches into countless thin streams and mixes throughout the entire glass. The ink has not disappeared from nature, but information about its original shape has been distributed among the movements of far too many water molecules. Decoherence is also somewhat like a quiet melody being played inside a stadium filled with conversation. The notes still contribute to the total sound, but the delicate relationship between them is quickly buried beneath thousands of other noises. To reconstruct the original melody exactly, we would need to know the state of nearly every sound in the stadium. In a quantum environment, the task is far more difficult because the number of interactions can become impossibly large. What is mainly dispersed is phase information, the feature that determines how quantum possibilities interfere with one another. While a small system remains isolated, the different parts of its state can preserve a relationship precise enough to create an interference pattern. After interaction with the environment, each possibility becomes linked to a different environmental state. The larger combined system can still be described by quantum mechanics, but the small part we observe on its own no longer displays clear interference. Entanglement plays a central role in this process. A photon reflected from an object does not simply fly away independently. Its state becomes correlated with the object's position or motion at the moment of interaction. After many collisions, information about the object is shared with the light, air, surfaces, and heat throughout the room. The chair no longer carries a separate quantum state of its own, but becomes part of a much larger network of interactions. Experiments with C70 molecules have demonstrated this process directly. These molecules can produce interference when they are prepared and isolated under suitable conditions. When they are heated, however, the molecules themselves begin emitting more thermal photons. Those escaping photons can carry information that distinguishes between the molecules' different paths, and the contrast of the interference pattern gradually decreases. There is no need to install a detector to track the path of every molecule. The mere escape of thermal photons into the environment is enough to connect the state with the outside world. As the temperature rises and more photons are emitted, the ability to preserve interference clearly weakens. This result shows that a system does not need to be observed by a human being before its visible quantum behavior disappears. The environment has already performed countless interactions before anyone reads the result. Compared with a C70 molecule, a chair contains an almost unimaginable number of atoms. It has a large surface area, a much higher temperature than the cold vacuum used in the experiment, and constantly emits enormous numbers of thermal photons. Every second, its surface also experiences countless collisions with air molecules. If the chair were somehow placed in a state involving two clearly separated positions, decoherence would occur so quickly that there would be almost no opportunity to observe interference. The chair has not chosen a position because it knows someone is watching. The room had already recorded information about its location through light, heat, sound, and collisions long before any observer appeared. Dust settles on its surface, air flows around its legs, and the floor bears the force of its weight. Each trace makes certain states more stable and easier for the environment to preserve than others. Those stable states are usually states with relatively well-defined positions. An object located in one particular place creates consistent traces in its surroundings. Photons reflect from the same region, air strikes the same surface, and the floor supports weight at the same location. Superpositions involving widely separated positions, by contrast, are quickly distinguished by the environment. The relationship required for interference therefore disappears from observation almost immediately. From this process, the classical world we experience begins to emerge. Objects possess relatively stable positions, motions, and shapes not because they have escaped quantum mechanics, but because the environment continuously selects states that can survive more reliably through countless interactions. A table maintains its form, a ball follows a trajectory, and a chair remains in one place because those descriptions are continually reinforced by the environment. We can say that the room is constantly measuring the chair, but the word measuring does not require an instrument with a display or a person reading the result. Any interaction that leaves behind information capable of distinguishing one state from another plays a similar role. A reflected photon, an air molecule changing direction, or a vibration traveling into the floor is enough to share information. The environment becomes an immense network of recorded traces without any need for consciousness. This helps separate quantum mechanics from a common but mistaken interpretation. Matter does not wait for a human being to look at it before deciding where it exists. The moon does not become a cloud of probability when no one is observing it, because it is constantly interacting with sunlight, cosmic radiation, dust, gravitational fields, and many other parts of its environment. Its position is recorded in countless physical traces, entirely independent of whether anyone opens a telescope. Even in a dark room, objects still emit infrared radiation because their temperature remains above absolute zero. Air molecules continue moving, colliding, and exchanging energy. Turning off the lights removes only part of the visible light. It does not isolate objects from their surroundings. Preserving a large quantum state would require many kinds of interaction to be reduced at the same time, something laboratories can achieve only with small systems and for limited periods. The chair can therefore still be regarded as a quantum system at the most fundamental level, but its state has become connected with too many parts of the room. The possibility of its being on the left and the possibility of its being on the right can no longer be brought back together to interfere like the two paths of a molecule. To accomplish that, we would need to control not only the chair, but every photon, every air molecule, and every vibration that had ever interacted with it. In practice, that task lies far beyond any technology available today. The transition from quantum to classical behavior is therefore not a sharply defined line. A large molecule can still produce interference if it is isolated well enough, while even a small particle can decohere rapidly if it interacts strongly with its environment. Size matters because larger objects usually create more interactions, but size itself is not a switch that turns quantum mechanics off. What matters is the rate at which phase information spreads into the surroundings. In very small systems, decoherence may occur slowly enough for experiments to follow it. As the number of components increases, each part gains more ways to exchange energy and information with the environment. The hotter, larger, and more exposed an object becomes, the harder it is to preserve its delicate state. The everyday world therefore lies in a regime where decoherence happens so quickly that our senses perceive only the final stable outcome. Quantum computers confront this problem directly. Qubits must preserve superposition and entanglement long enough for a calculation to be completed. But any uncontrolled interaction with the environment can degrade the quantum information. For this reason, the devices often need to be cooled, shielded, and calibrated with extraordinary care. Much of the effort in quantum technology is not aimed at creating new phenomena, but simply at protecting states that the environment can decohere very easily. Quantum sensors use that same sensitivity in a different way. A delicate quantum state can respond clearly to magnetic fields, acceleration, or extremely small changes in its surroundings. The very quality that makes it difficult to preserve also makes it a sensitive measuring tool. Scientists must find a balance between protecting the system from unwanted noise and allowing it to interact just enough with the quantity being measured. Decoherence explains very well why interference patterns disappear in large systems and why the world around us appears classical. It shows that quantum possibilities do not need to vanish from the entire universe. Information about them only needs to become so widely dispersed that they can no longer be recombined. Yet this explanation still leaves a deeper question about measurement. Why does one particular observation produce only a single result? Some interpretations regard decoherence as an important part of the process, but not the entire answer. Others place it within a broader picture involving branches, outcomes, or the collapse of the state. Objective collapse models instead propose that quantum states may change spontaneously through a genuine physical mechanism. There is still no final consensus about the deepest meaning of the theory, even though the experimental predictions of quantum mechanics continue to be confirmed with extraordinary precision. We do not need to choose an interpretation to understand the role of the environment in everyday life. The chair has a stable position not because consciousness forces it to, but because it has interacted with the room in countless ways. Each interaction makes different states less able to interfere, until the classical description becomes the only one that can be observed in practice. Our familiar view of reality emerges from a quantum foundation that is constantly exchanging information. The classical world, therefore, does not stand separately above quantum mechanics. It is the picture that emerges when countless quantum systems interact, lose phase coherence, and leave traces of one another. A large object still contains quantum structure within every atom, but its collective behavior becomes so stable that it no longer resembles an electron in a double-slit experiment. There is no mysterious transformation between the two scales, only an immense increase in the number of interactions. The chair remains where it is because the room has recorded its position too many times. Reflected light, emitted heat, moving air, and the force carried by the floor all tell the same story about where the object exists. Other possibilities may not necessarily be erased from every deepest description, but they no longer retain enough coherence to interfere before our eyes. The stability perceived by our senses is the result of this dispersal of information. The environment, however, has not always existed in the form of a room filled with air, light, and objects. In the very early universe, there were no chairs, planets, or stars recording one another's positions. Matter and radiation existed under entirely different conditions, and extremely small quantum fluctuations may have developed along a path that the present-day universe no longer allows us to observe directly. Those fluctuations may have been stretched to vastly larger scales, leaving tiny differences in the density of the early universe. Over billions of years, gravity continued to amplify them into regions where stars, galaxies, and galaxy clusters would form. The quantum world is not only hidden beneath the chair in the room, it may have left its imprint on the largest structures humanity can see across the sky. On a full-sky map of the cosmic microwave background, the universe appears as a vast pattern of adjoining colors. These bright and dark patches are not the locations of individual galaxies, nor are they clouds drifting through space. They represent extremely small temperature differences within a layer of light that was released when the universe was only about 380,000 years old. Beneath that seemingly simple image lie traces of the early variations that help determine where stars and galaxies would later be able to form. If that ancient layer of light had been perfectly uniform, matter in the early universe would also have been distributed almost evenly everywhere. With no region denser than another, gravity would have had few starting points from which to gather matter. Gas might have remained spread across space without easily collecting into clouds large enough to give birth to stars. The existence of galaxies therefore required the early universe to contain tiny differences, even though those differences were initially almost impossible to detect. At a very early stage, the universe was not transparent like the night sky we see today. The temperature was still too high for electrons to remain bound to protons, so matter existed mainly as a plasma of freely moving charged particles. Photons constantly collided with electrons and changed direction, preventing light from traveling far along a straight path. Space at that time resembled a dense, glowing fog in which radiation and matter continually exchanged energy. The universe continued to expand, and as space grew, the average temperature gradually fell. When the environment cooled to about 3000 Kelvin, electrons began combining with protons to form neutral atoms, mainly hydrogen and helium. As the number of free electrons dropped sharply, photons were no longer scattered continuously as they had been before. For the first time, light could travel across great distances without being trapped inside the hot plasma. The layer of light released at that moment is still traveling through the universe today. Over billions of years, the expansion of space stretched its wavelengths from hotter forms of light into the microwave range. Its characteristic temperature is now only about 2.7 Kelvin, far colder than when its journey began. Though weakened and stretched, it still covers nearly the entire sky, carrying the earliest image of the universe that humanity can observe directly. The cosmic background radiation is not exactly the same in every direction. Its temperature varies by only a few millionths of a degree. Differences so small that without highly sensitive instruments, the entire sky would appear almost uniform. Satellites such as Planck have measured these variations with great precision, producing detailed maps of regions that are slightly warmer or cooler. These temperature differences are connected to tiny variations in the density of matter and radiation in the early universe. A region with slightly greater density would exert slightly stronger gravity. The initial difference might have been extremely small, but gravity has the ability to amplify it over time. Surrounding matter would be drawn inward, making the region denser, which would then strengthen its gravitational pull even further. Over millions and billions of years, an almost insignificant variation could grow into a vast cloud of gas, a galaxy, or even an entire galaxy cluster. This process did not happen quickly, nor did it create structure in a single step. Matter first gathered in regions with deeper gravitational wells. Gas was then compressed, cooled, and formed the first stars. Stars collected into galaxies, while galaxies continued to assemble into clusters and superclusters. When astronomers examine the large-scale structure of the universe today, they see a network of long filaments of matter, dense nodes, and enormous empty regions. Dark matter played an important role in building this cosmic network. It neither emits light nor absorbs it in the same way ordinary matter does, yet its gravity affects the motions of stars, gas, and galaxies. According to the current model, dark matter began gathering early, creating gravitational regions into which ordinary gas could fall. It can be viewed as an invisible framework that helped luminous matter gradually assemble into the structures we can see. Although the cosmic background shows that early irregularities truly existed, it does not explain by itself why those irregularities appeared. To go further, physicists use a model known as cosmic inflation. According to this explanation, the universe experienced a period of extremely rapid expansion at a very early time. Space expanded at an enormous rate for an extremely brief interval, stretching regions that were initially very small to vastly larger scales. A tiny wrinkle in a sheet of fabric can help us picture this idea. If the fabric is stretched outward, the wrinkle also expands and occupies a larger area. Space itself is not a material sheet, and inflation was not an external force pulling it from outside, but the comparison shows how a very small structure can leave a much larger imprint when the space containing it expands rapidly. In the inflationary model, quantum fluctuations in fields at extremely small scales may have been stretched across cosmic distances. Before this expansion, the fluctuations belonged to a tiny quantum system. After space expanded, they became variations, spanning vastly greater scales. When inflation ended, these differences may have left imprints in the density of matter and energy, creating the seeds from which later structure would grow. This does not mean that a galaxy was once a tiny particle enlarged without changing. No single electron was stretched until it became the Milky Way. What expanded were fluctuations in fields and the density differences they produced. Gravity then gradually drew matter into the denser regions, forming complex structures over immense periods of time. A galaxy may contain hundreds of billions of stars, yet the location where it began forming may have been suggested by a difference smaller than any celestial body that exists today. The contrast between the early density levels was far too small to create a clearly defined structure immediately. Only after gravity had enough time to act could those faint ripples become the foundations of enormous stellar systems. The Milky Way also developed within a region that was once slightly denser than its surroundings. Over many generations, gas fell into the gravitational well, the first stars appeared, smaller galaxies collided and merged, and the larger structure gradually became more stable. The Sun formed only about 4.6 billion years ago, long after the original irregularities had begun to grow. Earth and our bodies lie near the end of a chain extending through almost the entire history of the universe. The heavy elements in our bodies did not emerge directly from the cosmic background or from inflation. Carbon, oxygen, calcium, and iron were created in later generations of stars, then scattered into space as those stars lost matter or exploded. Yet without the early regions of greater density, that allowed stars and galaxies to form, those processes of element production would have had nowhere to occur. The connection to primordial fluctuations is therefore indirect, but profoundly important. When we look toward the Milky Way, we are seeing the result of many layers of causes built upon one another. Quantum fluctuations may have created the original differences. Inflation may have stretched them to larger scales. Dark matter helped construct the gravitational framework, and ordinary gas cooled to form stars. Those stars went on to produce elements. Planets formed around some systems, and complex chemistry emerged wherever conditions allowed. The cosmic background does not merely reveal random temperature variations. The arrangement of warm and cool regions across the sky contains information about the composition, geometry, and expansion history of the universe. The characteristic sizes of these patterns reflect oscillations in the primordial plasma, where radiation pressure pushed matter outward while gravity pulled it inward. Those oscillations left imprints that can be compared with the predictions of cosmological models. Through this map, scientists can estimate the amounts of ordinary matter, dark matter, and other components in the universe. They can also test whether the original irregularities closely resemble the form predicted by inflationary models. Many observed features agree remarkably well with an origin in primordial fluctuations that were nearly random, yet distributed according to clearly defined statistical laws. Even so, agreement with the evidence does not mean that every detail of inflation has been confirmed. Science does not yet know which field caused the period of extremely rapid expansion, what energy scale it involved, or precisely how the process began and ended. Many different inflationary models can explain portions of the data. Determining which one comes closest to reality will require even more sensitive observations. One of the signals being sought is primordial gravitational waves, ripples in the structure of spacetime that may have been produced during inflation. If they exist with sufficient strength, they could leave a distinctive pattern of polarization in the cosmic microwave background. Experiments have measured these signals with increasing precision, but so far, no detection has been conclusively confirmed as direct evidence of primordial gravitational waves. The difficulty comes not only from the weakness of the signal, dust within the Milky Way, radiation from astronomical sources, and other effects can create polarization patterns that are easily mistaken for the signal being sought. Any initial result must therefore be tested across multiple frequencies and with several independent instruments. In cosmology, separating ancient light from layers of interference closer to Earth can be just as difficult as constructing the theory itself. Nor can we say that inflation is the only possible explanation for every feature of the early universe. It remains a powerful and widely used framework because it addresses several problems at once and produces predictions that agree well with the data. Yet other ideas are still being studied, and inflation itself contains unanswered questions. A clear boundary must always remain between what has been observed and the explanation proposed for its origin. What has been firmly observed is that the early universe was not perfectly uniform. The cosmic background contains tiny variations. The present-day distribution of galaxies has structure, and gravitational models can connect these two pictures across the history of cosmic development. The physical mechanism that truly produced the first variations, however, remains an active area of research. Inflation and quantum fluctuations provide a compelling explanation, but not yet a final answer to every detail. Time transformed tiny differences into a structured universe. Gravity did not create matter from nothing. It simply gathered what already existed into different regions. Places that were slightly denser attracted more matter, while regions containing less matter gradually became emptier. Through this slow amplification, the cosmic web formed without any predetermined blueprint for each individual galaxy. A small seed does not contain the complete shape of a forest, but it provides a starting point for a long process of growth. Primordial fluctuations did not already contain the forms of the Milky Way, the Sun, or Earth. They created only the initial differences. Gravity, gas, dark matter, and billions of years of evolution then built the final structures. It was this immense passage of time that transformed tiny probabilities into a sky filled with galaxies. Following this chain of causes, the quiet room where our journey began also has a history extending back to the early universe. The atoms in the walls were formed from matter that once existed within clouds of gas in the Milky Way. The Milky Way developed in a region whose density was more favorable than that of its surroundings. That region, in turn, may carry traces of extremely small fluctuations that existed before the first star ever began to shine. Quantum mechanics therefore does more than create the structure of atoms or govern reactions inside the sun's core. According to current cosmological models, it may have left an imprint on the distribution of matter across the greatest distances humanity can observe. The rules commonly introduced through electrons and photons may be connected to the positions of galaxy clusters separated by millions of light years. This connection does not mean that the universe is one enormous object visibly interfering with itself. The original fluctuations passed through expansion, decoherence, and many stages of development before becoming classical differences in density. By the time the cosmic background was released, their traces had appeared as tiny temperature variations. Gravity then took over, continuing to amplify them according to laws that can be observed. But to understand what those quantum fluctuations were fluctuations of, the image of separate particles begins to feel incomplete. Electrons, photons, and other particles may not be the final independent building blocks resting within space. In the modern description, each type of particle is associated with a field extending everywhere, while a particle is an excited state that appears within that field. If this view is correct, the space between galaxies is not a completely empty container. Even where no detectable atoms or photons are present, quantum fields still exist in their lowest energy states. The fluctuations that may have planted the seeds of cosmic structure could be signs that empty space always possesses a deeper structure than its appearance suggests. The journey from this room to the galaxies has therefore not yet reached the deepest level. Behind matter, light, and even the earliest ripples may lie a broader description in which fields exist at every point in space. To enter that final layer, we must move into a place where there seems to be nothing left to observe and ask whether a completely empty region is ever truly without structure. Imagine a box from which all the air has been removed, sealed off from light and cooled until almost no significant thermal motion remains. Intuitively, there seems to be nothing left inside it to observe. No gas molecules, no dust, no visible light, and no objects drifting through. If any place deserves to be called completely empty, this would appear to be it. But modern physics does not describe empty space so simply. Removing every observable particle does not mean that all physical structure disappears. In quantum field theory, space still contains fields even when they are in their lowest energy state. The vacuum is therefore not an absolute absence, but the ground state of a system that still possesses structure. To understand this, we need to change the way we picture particles. In everyday life, a particle may bring to mind a speck of dust, a drop of water, or a very small object located somewhere in space. Quantum field theory offers a different picture. The deeper foundation is not a collection of separate little spheres, but fields extending throughout space. A particle appears as a particular excitation of its corresponding field. The electron field does not exist only where an electron happens to be. It is present everywhere, while an electron is a stable excitation of that field. A photon is not a tiny marble of light completely separate from everything around it, but a quantum excitation of the electromagnetic field. Other kinds of particles are described by other fields, each with its own properties and forms of interaction. The image of an ocean and its waves can make this idea easier to grasp. A wave may appear in one location, travel, and carry energy across the water, but it does not exist entirely apart from the ocean. Without the surface of the water, there would be nowhere for the wave to appear. In a similar way, a particle can be viewed as a distinct state within a broader field, although a quantum field is not a real fluid filling space. This perspective makes the word empty more difficult to define. A region containing no actual electrons still contains the electron field. A region containing no actual photons still contains the electromagnetic field. These fields may be in their lowest energy states, but the lowest possible state does not necessarily mean absolute silence. Even in the ground state, quantum quantities can retain fluctuations and their own limits of uncertainty. We should not imagine these fluctuations as tiny particles constantly springing out of nothing and then disappearing. Stories about virtual particle pairs appearing and annihilating can sometimes be useful in introductory explanations or certain calculations, but they can easily become far too literal. Virtual particles are not real marbles that can be directly observed, and the quantum vacuum is not a boiling pot filled with countless temporary objects. One indication that the vacuum state has physical consequences is the Casimir effect. Place two uncharged metal surfaces extremely close together in a vacuum. When the distance becomes small enough, they can experience a weak force that tends to draw them toward each other. This force has been measured in many experiments and becomes significant in micro and nanoscale electromechanical systems. The origin of the force does not need to be described as virtual particles pushing more strongly from outside than from between the surfaces. A more careful explanation relies on the boundary conditions that the two surfaces impose on the electromagnetic field. Between them, only certain modes of field fluctuation are allowed, while a different set exists outside. This difference changes the energy of the system and produces a measurable force. The two metal surfaces do not create fields from nothing, nor do they prove that empty space contains an invisible substance resembling a gas. They simply change the ways the electromagnetic field can be arranged within the narrow region between them. The Casimir effect, therefore, shows that the vacuum can respond to physical conditions rather than serving as a completely passive background with no structure of its own. At everyday scales, the Casimir force is far too weak for us to feel, but in extremely small devices, where the distance between components may be only a tiny fraction of the width of a human hair, it can affect motion. Engineers designing microelectromechanical systems must account for interactions like this to prevent surfaces from sticking together or functioning incorrectly. An effect arising from the vacuum state can therefore become a practical engineering concern. The Higgs field extends this story to the origin of the masses of elementary particles. This field is believed to be present throughout space, and different particles interact with it to different degrees. The strength of that interaction is related to the particle's rest mass. The discovery of the Higgs boson strongly confirmed that the Higgs field is more than a mathematical idea introduced merely to complete the model. However, it would be inaccurate to say that the Higgs field creates all the mass of every object. An electron receives its mass through its interaction with the Higgs field, but most of the mass of protons and neutrons comes from the energy of the strong interactions among the quarks and gluons inside them. Because an object such as the human body contains enormous numbers of protons and neutrons, most of its mass cannot be explained by the Higgs field alone. This reminds us that an answer that is correct at one level may not be complete at another. The Higgs field helps explain why many elementary particles possess rest mass. While most of the mass of ordinary matter emerges from binding energy and internal motion within atomic nuclei, mass is not a substance poured into an object, but a property arising from several fields and interactions working together. When quantum fields are placed in relatively flat space-time and conditions are not too extreme, the theory produces predictions of extraordinary accuracy. Near a black hole, however, space-time is strongly curved, and the boundary between the region from which escape is possible and the region from which nothing can return becomes critically important. Here, quantum mechanics and gravity must appear within the same problem, even though the two theoretical frameworks have not yet been fully unified. By studying quantum fields near an event horizon, physics predicts that black holes are not completely black. They may possess a temperature and emit extremely faint radiation, now known as Hawking radiation. For astronomical black holes, the predicted temperature is extraordinarily low, causing this radiation to be overwhelmed by many other sources of radiation in the universe. So far, no direct observation from a real black hole in space has been conclusively confirmed. Even without direct measurement, this prediction remains profoundly important. It connects quantum mechanics, thermodynamics, and gravity within a single phenomenon. An object once thought only to absorb matter may gradually lose energy and mass over time. If the process continues long enough, a black hole could, in principle, evaporate. This leads to the black hole information paradox. Quantum mechanics generally requires information about the state of a system to be preserved in an appropriate way. But if matter falls into a black hole and the black hole later evaporates into nearly thermal radiation, where does the original information go? Is it subtly encoded in the radiation, preserved at the event horizon? Or does the problem require us to change the way we understand spacetime? Many lines of research have proposed different answers, but no single solution has yet been fully verified. Some theoretical results suggest that information may not truly be lost, though the way it is preserved within a complete description remains a profound problem. This paradox is not only about black holes. It reaches into the question of whether the fundamental rules of quantum mechanics continue to hold under conditions of extremely strong gravity. Empty space also leads to another mystery on the scale of the universe. Observations of distant galaxies show that the expansion of the universe is accelerating. The component responsible for this behavior is commonly called dark energy, but the name describes only its role, not its true nature. One possibility is that dark energy is connected to the energy of the vacuum, yet directly identifying these two concepts creates an enormous theoretical gap. Simple calculations of vacuum energy in quantum field theory can produce results vastly different from the value inferred through cosmology. The discrepancy is so great that it has become one of the most difficult problems in modern physics. Perhaps the calculations are incomplete. Perhaps another mechanism cancels most of the energy. Or perhaps dark energy is not simply vacuum energy in the most straightforward sense. What is more certain is that the universe is undergoing accelerated expansion, while the deepest cause remains unknown. The quantum vacuum produces measurable effects in small systems, but that does not automatically prove that it is the source of dark energy. There is a compelling theoretical connection between the two problems, but no complete bridge has yet been built between them. Here, two of the greatest achievements of modern physics stand side by side without merging into a single picture. Quantum mechanics and quantum field theory describe particles and microscopic interactions with extraordinary precision. General relativity describes gravity as the curvature of spacetime and explains the motion of planets, stars, galaxies, and black holes. Each theory succeeds within its own domain, but when pushed into extreme conditions, their combination remains incomplete. A theory of quantum gravity would need to describe both spacetime and quantum fields within the same framework. Many approaches have been developed, from models that treat elementary particles as extended structures to ideas suggesting that spacetime may be built from discrete quantum units. Even so, no theory has yet been fully confirmed by experiment and accepted as the final answer. We also do not know whether spacetime remains continuous down to arbitrarily small distances. It may be meaningful to keep dividing space into smaller and smaller regions without limit, but it is also possible that, at an extremely small scale, the concepts of position and distance must be changed. If spacetime has a quantum structure, then the very foundation on which fields exist can no longer be treated as a fixed background. This question changes the way we think about empty space itself. Space may not simply be an empty container holding matter and radiation. It may be a dynamic part of nature, able to curve, expand, contain fields, and perhaps possess a quantum structure of its own. In this picture, matter is not merely placed into space from the outside. It appears as states of fields existing within the structure of space itself. Yet the deeper we go, the more unanswered questions appear. In what sense does the vacuum possess energy? How does information escape from a black hole? Is spacetime quantized, or is it a continuous foundation? Does quantum mechanics need to be modified under strong gravity, or does it simply need to be placed within a broader theory that we have not yet discovered? None of these questions diminishes the value of what is already known. The Casimir effect has been measured. The Higgs field revealed its corresponding particle in accelerators. The predictions of quantum field theory match experiments with extraordinary precision, while general relativity continues to pass demanding tests. The gap lies in the fact that these achievements have not yet been joined into a complete description that works under every condition. Our journey began at the surface of a table, where electrons cause matter to resist being passed through. It entered the atom, followed photons into light, descended into the core of the sun, crossed through white dwarfs and neutron stars, and expanded toward the irregularities that planted the seeds of galaxies. Now the story pauses in a place where no object seems to remain. Yet even there, fields may preserve their ground states and produce measurable effects. The final destination is therefore not a closed answer. We do not yet know whether the deepest layer of nature is built from fields, from a quantum structure of space-time, or from a framework that has not yet been discovered. What we can carry with us is that empty space no longer appears to be a meaningless region between objects. It may be one of the most complex parts of the entire universe. The imaginary box from the beginning still contains no air, dust, or visible light. But it no longer resembles a place where absolutely nothing exists. Fields remain present, the vacuum state retains structure, and physical conditions imposed upon it can create measurable effects. What appears to be complete absence may simply be the lowest state that nature allows us to observe. As we return to the quiet room where the journey began, the bed, the walls, and the faint light of the clock remain in their familiar places. They are made from excitations of fields, held stable by quantum rules, and existing within a space that may never be truly empty anywhere. The journey has carried us very far, yet the deepest question remains open. Beneath everything we call matter, light, and empty space, what else is nature still keeping hidden? After traveling through atoms, light, dead stars, and the earliest traces of galaxies, we return once more to the quiet room where we began. The bed still supports your body. The walls remain standing in the darkness. On the face of the clock, each second continues to pass with a steady rhythm, as though nothing has changed. Only the way we see these familiar things is different now. The tabletop before you is not a solid block assembled from atomic marbles pressed tightly together. Most of the mass in every atom is concentrated inside an extremely small nucleus, while the size of matter is determined mainly by the surrounding electron region. When your hand rests on the surface, electrons in your skin and in the table respond to one another, creating the force that prevents the two objects from passing through. The sensation of solidity emerges from interaction, not from perfectly solid surfaces making direct contact. Inside the atom, there is no miniature planetary system moving along perfect circles. Electrons exist in states with particular shapes and energy levels, described by probabilities rather than continuous paths. An electron can transition into a lower state, but only as far as the lowest level the atom permits. These limits, strange as they may seem, are precisely what prevent the structure of matter from collapsing. When many atoms come together, the story is no longer only about the attraction between electrons and nuclei. Electron regions change, extend across multiple atoms, and form new bonds. From these arrangements emerge water, proteins, DNA, the pigments in leaves, and the molecules drifting away from a hot cup of coffee. The scents, flavors, and colors received by our senses all begin with the way electrons are distributed and respond to their surroundings. Light carries the journey beyond the atom. A photon may be detected at a single point like a particle, yet the possibilities leading to that point can still interfere in a wave-like way. Electrons and molecules reveal similar behavior when they are protected well enough from the environment. Nature is not required to choose between two familiar pictures. It is our images of waves and particles that fail to describe it completely. Beyond the window, sunlight carries energy that began deep within the star's core. There, protons with the same electric charge constantly repel one another. Yet quantum mechanics preserves a small probability that they can approach closely enough to react. Each individual opportunity is extremely rare, but the sun contains so many protons that the process continues without interruption. From that tiny probability, light reaches leaves, causes water to evaporate, drives the winds, and enters most of the food chains on Earth. Even when a star can no longer produce energy as it once did, quantum rules continue to determine its fate. Inside a white dwarf, electrons cannot crowd freely into the same state, so matter produces pressure that resists gravity. If the remaining core is more massive, it may collapse into a neutron star, where more mass than the sun is compressed into an object only a few dozen kilometers across. Principles governing unimaginably small particles can therefore support an entire star. And yet the room around us does not clearly display these quantum states. The chair does not appear in two places because it is constantly colliding with air, reflecting light, releasing heat, and transmitting vibrations into the floor. Information about its position has spread into the environment along countless paths before anyone ever looks at it. Quantum behavior has not ceased to exist. Only the ability of different states to interfere has been dispersed too quickly. Far beyond the chair, beyond the Sun and the Milky Way, the oldest light in the universe still preserves extremely small temperature differences. According to current models, those variations may have begun as quantum fluctuations stretched across the early universe. Gravity amplified them over billions of years, gradually gathering matter into stars, galaxies, and vast cosmic networks. No individual fluctuation already contained the shape of the Milky Way, but it may have helped determine where the process of formation would begin. Even the space between objects no longer resembles a completely empty box. Quantum fields remain present even when no real particles can be detected, and the vacuum state can produce measurable effects. Although we do not yet know whether fields represent the deepest layer of nature, modern physics shows that the absence of matter does not mean the absence of all structure. Quantum mechanics, therefore, does not turn the world into a place where anything can happen without restriction. It distributes possibilities according to precise laws, determining which states can exist, which remain stable, and how systems exchange energy. From a foundation described by probability, atoms preserve their form, molecules remain bonded, stars continue to shine, and matter creates surfaces strong enough to support the body. The stability around us did not appear only after nature removed every uncertainty. It emerged from the way quantum possibilities are limited, combined, and continually brought into contact with the environment. A tiny probability can illuminate a star when repeated countless times. A principle governing electrons can resist the gravity of an entire celestial body. An early fluctuation can leave its imprint on the structure of a galaxy. The room remains quiet, but that quietness no longer means stillness. Within the walls, the tabletop, the air, and the body, fields and particles continue exchanging energy according to laws that cannot be seen directly. The familiar world does not stand outside quantum mechanics, nor is it an exception that has escaped its strangeness. The universe remains stable, at least in part, because those strange rules are quietly at work within everything around us.